In numerical analysis, stability is often an illusion of resolution. What looks like an impenetrable, monolithic structure at one scale often shatters into microscopic fragments the moment you look closer. To understand how completely a numerical consensus can collapse, we are looking at the twisted bird map transfer operators. These map the dynamics of an abstract space across a highly structured boundary subgrid. This chart shows the exact parameter space under investigation. The vertical axis represents three specific kernel families: WBA, Lorentzian, and alien. The horizontal axis maps 10 specific boundary values for the parameter epsilon, generating 30 precise intersection points to test. In previous tests at Ulam grid resolutions of 1024 and 2048, the output of this operator across all 30 intersections appeared perfectly stable. It was universally classified as regime A. This is a visualization of that regime A signature. The invariant-density proxy collapses into a pure Dirac-like single-cell spike. There is exactly zero background oscillation, and the surrounding grid space registers as entirely empty. The standard volume norms used to measure these matrices are blunt instruments. They capture the mass of the main spike, but lack the mathematical sensitivity to detect microscopic, sub-cell activity occurring in its shadow. The N=2048 grid created an incredibly convincing illusion of a stable, single-cell architecture, but that stability was entirely dependent on the limits of the grid itself. Paper 47 executes a new experiment. It doubles the Ulam matrix resolution to N=4096. Across all 30 Monte Carlo executions on the boundary grid, the resulting data executes a complete reversal of the established consensus. At this higher resolution, the single monolithic bar fractures. The previously empty surrounding cells register strictly positive mass, meaning the discrete spike is no longer isolated. This reaction occurs across every tested kernel and epsilon char. It is a total structural breakdown of the prior mathematical state. The previously defined regime A is entirely falsified. Every boundary cell has shifted into a newly categorized state known as regime B. To measure the precise architecture of this newly revealed grid behavior, classic numerical tools are useless. They cannot map the geometry of these microscopic fractures. Resolution scaling exposes hidden numerical artifacts. The lower resolution grids alias the data, and only by doubling the computational density could the true topology be mapped. To bypass standard volume norms and analyze these hidden states, the researchers rely on the spike-quotient battery, a sequence of 5 strict mathematical filters. This heat map tracks the battery's output across all 30 parameter pairs at the 4096 resolution. Every single cell triggers positive readings, confirming the total shift into regime B. The first filter, VOP, quantifies the volume of non-zero mass in the spike complement. Next, EAE quantifies how widely that residual mass diffuses horizontally. BV-COMP tracks variation, quantifying sharp structural vertical step heights. Finally, SQOSC and CR-suppress verify containment, ensuring the complement is tightly grouped. It is crucial to note these are purely algebraic operations executed on finite-dimensional vectors. They are not continuous integrals. These 5 functionals provide a mechanical, explicit method to mathematically differentiate a genuinely pure single-cell spike from one hiding a highly concentrated microscopic tail. Detecting the microscopic tail is only the first step. The diagnostics must now be used to precisely measure the physical width of that tail across the grid. To accomplish this, the functional outputs are run through specific algebraic inversions, mapping the raw data back to integer-based subgrid cell counts. The inversion for entropy calculates the KEAE width, translating entropic spread into distinct physical grid cells. The complementary KBV width takes 1 + 2 divided by BV-COMP, generating a second cell count based purely on vertical gradient data. These two metrics provide independent algebraic pathways to infer the structure of the spike complement. If the hidden cluster is uniform and tightly organized, both of these inversion formulas will calculate roughly the same integer value. This algebraic inversion translates abstract grid energies into literal, observable cell counts. It gives us the exact mathematical topology of the clusters hidden in the data. Applying these two inversions across all 30 boundary cells uncovers drastically different architectural typologies within regime B. The Lorentzian cell at an epsilon value of 1.02 serves as a prime example of a coherent, tightly supported substructure. This chart maps the two calculated widths. For the Lorentzian cell, both the entropic and variation widths perfectly align, reading between 2 and 5 cells. The structure is dense and highly uniform. But the WBA kernel at an epsilon of 0.70 exhibits entirely different behavior. Here, a massive numerical mismatch occurs. The variation width remains tightly locked in the single digits, while the entropy width explodes into the hundreds. We define this extreme mismatch as the divergence crisis, which can be tracked by calculating the logarithmic ratio between the two independent metrics. A high divergence indicates that the entropy metric is catching a very broad, low-amplitude spray of data, while the variation metric anchors itself firmly to a steep, localized central core. Regime B is not monolithic. It houses both tight core clusters and broad entropic sprays, proving the boundary subgrid contains complexity entirely missing from previous models. At this stage, we must establish a strict epistemological boundary regarding these findings to avoid a very common professional trap. All the data, widths, and structural typologies mapped by the spike-quotient battery exist strictly within the finite n equals 4096 Ulam discretization. This research makes zero claims regarding the true continuous geometry of the invariant density as n approaches infinity. We have not proven that the regime A single-cell spike is mathematically impossible in the infinite continuum limit. Extrapolating numerical grid artifacts directly into continuous physics is a fatal methodological error. This data must be analyzed entirely on its own finite algebraic terms. The experiment yields a definitive result. At a resolution of 4096, the spike-quotient battery universally falsifies the single-cell regime A across the entire boundary grid. The data isolates specific high-signal targets, namely the Lorentzian corner and the alien epsilon 0.76 cell, which exhibit the cleanest, most coherent cluster topologies. The immediate next step is to push the boundaries of available computational memory, extracting Ulam densities at resolutions of 8,192 and 16,384. This extreme resolution scaling is necessary to test whether the divergent entropic tails are stable features of the phase space, or merely transient grid artifacts that will dissolve at higher densities. The purely isolated single-cell spike was a low-resolution illusion. The true, complex map of the boundary subgrid is only just coming into focus.